So I first want to start, of course, by thanking the organizers for inviting me here, giving me the opportunity to speak, but also to actually give me the opportunity to be here. I'll confess, as many other speakers, it's my first time, so I'm really very happy to be here. And today I will report on joint work with Yassine El Mazzouz from Aachen, Marvin Hahn from Dublin, Gabriele Nebe from Aachen, and Bernd Sturmfels from Leipzig and Berkeley. And this is somewhat a larger project that we started together, and it started living at the interface between representation theory and tropical geometry, but it took various twists that I hope to show you later. So let's start with the setting. So K throughout the talk will be a discretely valued field. OK will denote the valuation ring, which consists of the elements of valuation, non-negative valuation. It is a local ring with unique maximal ideal given by the elements of positive valuation. And then we fix a uniformizer, so an element of valuation 1 that generates the maximal ideal, and all the other ideals will be powers of this maximal ideal. And this valuation we can also extend to taking vectors with coefficients in K or matrices. And for now, really this valuation could be anything. So you can take Q with the three-adic valuation, or you can take formal Laurent series with the usual valuation. And it really doesn't matter if the residue field is finite or not. Later I want to do some counting, but I will tell you when this happens. And also to set some notation, for me today a lattice or an OK lattice in K to the D is a positive integer, of course, will be a free OK submodule of full rank. And an order is a lattice in K to the D times D, so D by D matrices with coefficients in K, that is also a ring. And for me, rings have the identity element, and we call it maximal if there are no proper orders contained in it. And a lambda lattice will be a lattice in K to the D that is also a module over lambda. So I will sometimes say that it's a lambda lattice, sometimes I will call it a lambda stable. So here are some examples. So if we take OK to the D, so this you can think of as taking just the standard basis in K to the D and allowing only coefficients that come from the valuation ring. This is called the standard lattice in K to the D because it's associated to the standard basis. And OK to the D times D, so the D by D matrices with coefficients in OK, these form a maximal order in K to the D times D. And if we now want to look at its stable lattices, well, the standard lattice is a stable lattice, and all the scalar multiples by non-zero elements in the field will also be stable because scalar multiplication commutes with the elements of the order. And I'm only writing those that come from powers of the uniformizer, because these are the really different ones from the OK to the D. And it is also true that these are all the stable lattices that you can get. So when two lattices differ by a non-zero scalar, we will call them homothetic. And this defines an equivalence relation on the lattices. And we call the equivalence class, we denote the equivalence class of a lattice under homothety with those square brackets. Okay? And if L is a lattice in K to the D, I'm gonna denote by end OKL what is really the stabilizer of L inside K to the D times D. This is the notation that we used in the papers. We called it the endomorphism ring, so the endomorphism ring as a lattice in K to the D. Okay, so this is just the stabilizer. And so if we take two lambda lattices, L and L prime, well, first of all, any homothetic lattice will be also a lambda lattice, so stable under lambda, as we saw before, and homotety preserves the endomorphism rings. Also, since these lattices are modules over lambda, then taking intersections and some also are operations that preserve this property. Okay, so since we saw that if we want to study the lambda lattices, whenever we have a lattice, we have also its homotety class immediately contained in it. Well, instead of looking at the lattices, we're going to be looking at the homotety classes of stable lattices under an order. And this I'm going to denote by Q lambda. So in particular, as an example, well, lambda is maximal if and only if the collection of stable homotety classes has cardinality 1. Okay, so you can think of maximal orders to be the same as endomorphism rings of lattices. And a property that we have is that if an order lambda 1 is contained in lambda 2, once we take the stable lattices, this inclusion reverses. However, the other implication is not true. I will show you an example. And those orders that are really determined by the collections of their stable lattices, we call closed. So these will be the same as the intersection of the endomorphism rings of the lattices that they stabilize. So here is a remark. This is the same as I just said. For closed orders, the reverse implication holds. So closed orders are really completely determined by their stable lattices. So let me give you an example. Okay, we start with 2 by 2 matrices with coefficients in K. And now we actually take two orders that are defined in the following way. So they will both have coefficients entries in OK. But now the first order, we define it such that the 2, 1 entry, actually, it will always be 0 modulo the uniformizer that we picked. So it means that the valuation in the 2, 1 entry will be at least 1. Yeah, and this is the order that you get written as in matrix representation. And now we can define an order lambda 2 contained in lambda 1, on which we add additional equivalence relations on the diagonal. So we also ask that the 1, 1 entry and the 2, 2 entry will be equivalent modulo the uniformizer. Okay, so now what happens is that these two guys have the same collection of stable lattices. From now on, let me just say stable lattices. What I mean is really the homotety classes of the stable lattices, but just to save some voice. So they have two homotety classes of stable lattices. These are given there. But you see, lambda 1 is closed, but lambda 2 is not. If they were both closed, then we would have to be the same. Okay, so this was an example just to show that the other inequality, the other implication does not hold in general. And really the main goal of the project when we started was the following. We want to understand closed orders through their collection of stable lattices, or the other way around. Once we have the order, we want to be able to compute the Q lambdas. And I hope to convince you today that the right way to do this is via the language of Bruhat-Tits buildings. But I'll get there. Let's get warmed up a bit more first. And I'm going to soon be talking of a particular type of orders called graduated. So for this, let me fix a basis in K to the D. So say maybe the standard basis, doesn't matter. And then for each integral vector of length D, I can define a lattice. What do? I just scale the basis vectors by powers of the uniformizer, and the exponents are encoded in the vector. So you see it there, and I will write, if U is the exponent vector, I will write LU to mean precisely that. Yes?
If you fix a Q lambda, can you count how many homotety classes of lambda give rise to a given Q lambda?
If I fix a lambda,
if you fix a Q lambda, you said there can be multiple homotety classes that give rise to the same endomorphism. Can you count how many there are?
How many? Yes. Right.
So you said there are at least two homothetic classes that have the same Q lambda. So are these the only two? Can you count how many there are?
So you're asking, once I fix a Q lambda, count all the orders such that this is the collection of homothetic classes. We haven't addressed this question. It's also modulo what do you want to count this? I mean, do you want to count it modulo conjugation, modulo isomorphism? I mean, because these objects can also move. So it's an interesting question, definitely, but it's not something that we did so far. Yeah, no. Okay, but you will see later that these, some of these orders are constructed in such a way that you can say very much about them. But let me get through that, and then maybe we can talk afterwards. Okay, right, so the lattices that I build from a fixed basis and an exponent vector, I will call diagonal with respect to this basis. And I will say that two lattices and better a collection of lattices as compatible bases if they are diagonal with respect to the same basis. So here's an example. If we pick E to be the standard basis, then and the vector U to be the all zero vectors, what we recover is the standard lattice. And here is the reason why I said better than two lattices, let me talk of a collection of lattices, because it is not difficult to show that two lattices are always diagonal with respect to the same basis. And this we will use later. So we can always find a basis such that we write the two lattices as diagonal with respect to this basis. And now, if you remember the example with the lambda 1 and lambda 2, the closed and non-closed order, we wrote down the homothetic class of the stable lattices. So two representatives are there of those classes. And we could have written them as L01 and L00 with respect to the standard basis. And the lambda 1 order, we could have written in this other form. So as all the matrices 2 by 2 with coefficients in K, such that the entry-wise valuation is at least that matrix M of integers. Okay, so when I write that, I really mean each entry corresponding to each entry. So this brings us to a more general concept. So this was an example. Let's try to make it more general. So if we have a matrix D by D with coefficients in Z, then we can define a set, lambda M, so my matrix is M, and really think of this matrix M as a matrix of valuations. These are the matrices D by D that have valuation at least M. This is by construction contained in K to the D times D, and it is lattice in K to the D times D. And why is it a lattice? Well, the point is that I don't allow infinity in the entries of M. So I really will get full rank here. So here's another example. So if I take M to be 0, then I just recover the matrices with coefficients in the valuation ring. Say now we want to look at a different example, and we really specify what the valuation is, what the field is. We take K equal to Q, D equal to 3, and we take the valuation to be p-adic valuation for some prime P. It doesn't really matter. And we now take X to be that matrix there. So it has all ones in the matrix, but a P in the top right corner. The valuation of this matrix is given by that matrix M. Right? So I have all zeros everywhere and a 1 in the top corner. Now, if I square my matrix X, that is what I get on the right. And if I take its valuation, it will, of course, depend on what P is. But the top right corner will always, the valuation will always be 0 because the entry is congruent to 1 modulo P. And if you now stare at them, you will see that the valuation of X squared is not at least M. So this is an example in which lambda M is a module, but it's not a ring. Okay, so it is, of course, natural to ask, we live in a ring, when is it a ring? But it's also good to be aware of the fact that not always these guys will be rings. And when they will be, there will actually be orders in k to the d times d. And we call them graduated following Pleskin and Sassenhaus, but in the literature, these orders can be found also under the names of monomial, tiled, or split. So we started from here. Later, when I will be mentioning Pleskin, I really refer to the book of Pleskin from 83, where he credits also Sassenhaus for the results. So they started the study of graduated orders, and what we did, we interpreted and extended their results to start in the language of tropical geometry. So here is a proposition that tells us exactly when lambda n is an order. So first of all, we'll have to have that the matrix M has zeros on the diagonal, because we want to include the identity element. And those triangular inequalities on the right will make sure that our modulo is multiplicatively closed. And I will decorate Z with a 0 from now on to mean that we take matrices that have the zeros on the diagonal, because this is anyway one of our requirements. And so if we look back at the examples that we saw, well, the very first example with the lambda 1 had that matrix, defining matrix, 0, 0, 1, 0. And in that case, we did have a ring. While the example that I showed you where the lambda m wasn't a ring had valuation matrix, this second m. And you see that if you compare indices 1, 2, 2, 3, and then 1, 3, in that inequality, that is not satisfied because the sum of m1, 2 with m2, 3 is 0, while m1, 3 is 1. Okay, and we will see soon that these are closed orders, so these are sort of like the simplest class of orders to study, and this is also where we started. All right, so I'll have a sip and then I'll continue with this. I'll let you stare at it for a second. So Pleskin and Sassenhaus already had determined what the stable lattices were under graduated orders, and they described them very explicitly. They said if we start with a graduated order with matrix M, then actually the stable lattices, they will all be diagonal. The exponent vectors will be related by those inequalities over there, and these lattices as lambda m modules will be isomorphic if and only if their homotopy classes will be the same. So we really understand completely what is happening here. And here is an example, okay? If we take M to be that matrix over there, then what happens here is that in this picture, the points that have integral entries precisely describe the homotopy classes of the stable lattices. And you see, since this example is for d equal to 3, but I'm working up to homotopy, which means if I have an exponent vector, I can add the all ones vector. The homotopy classes doesn't change because that means multiplying by p, yeah, by the uniformizer. And this holds for any power. So whatever scalar multiple of the all one vector that I add, I preserve the homotopy class. So this is why this picture is drawn in the plane given by z equal to 0. Because this we can always do. We can always pick a representative for our exponent vector in a hyperplane, okay? In a given one. Very good. So this is first step of the picture. Let's see it one more, but in a different language. So that guy, I forgot to comment, but if you stare at it, that is a polytope. And you could ask, is this always the case? That this is always a polytope? Well, the answer is yes. And actually, it's even more. So if we work in RD modulo the R times the O1 vector, which we can do because we're looking at homotopy classes anyways, this is the natural setting for tropical geometry. Okay, and if we set those inequalities that we had for the determination of the stable lattices, what we get is something that is called a polytrope. So this is a polytope both in the language of tropical geometry and in the usual sense. So this is pretty cool. And this is always true. So it has these two types of convexities. And I will tell you more about this. But this means that in the proposition that we had before, now we can translate in purely tropical geometric terms, in the sense that we can say that the collection of stable lattices under a graduated order is in one-to-one correspondence with the integral points of the associated polytrope.
Sorry, could you please say again how the polygons connected to the matrix? You said that these things correspond to lattices, so you're thinking of diagonal lattices with...
Yes, correct. Because all these graduated orders, they have a basis fixed. Yeah, so you can, of course, you can change bases, and you don't have to work always with the same basis, but then you can really write them out in such a way that the valuations correspond one-to-one to a matrix, and then you can build the polytrope exactly from the matrix using the conditions that give you the stable lattices. Okay, so I told you this was all translated in the language of tropical geometry, so let me just quickly tell you what this means. Well, when doing tropical geometry, we work with different operations over R, and plus can be taken either to be min or max. Normally one makes a choice, but for this project we really need them both. And multiplication is given by sum. And the reason why we need really both min and max plus, you see it there, right? I told you if we have stable lattices, we can add them and intersect them, and we still get stable ones. And those are given, if we have diagonal lattice, precisely by taking, in the case of the intersection, the max plus, and in case of addition, the min plus. And these operations now we can use also to define products of matrices. So how does it work? Does this work? Well, you think of multiplying the matrices as you would do normally, but now when you have to multiply, you use a tropical multiplication. When you have to add, you use a tropical sum. And I am writing, see here these examples, a bar at the top if we use the max plus, and a bar at the bottom if we use the min plus as the addition. So if I multiply m with n using, well, let's see them both at the same time. So if I multiply m with n, let's see the first, the 1 entry, what I would get. I would have 0 times minus 2, this is sum, okay, so it's minus 2, plus, which to be determined, 1 times 3, which is 4. So I have minus 2 and 4. And now either I take the max in the first one so that I get 4, or I take the min and I get minus 2 below. And this is how it goes. Okay? So it's a bit confusing at first, but then, you know, once you get into it, then that is just like multiplying matrices as we know them. So why do we need this? Well, now we really can compactly describe several of the properties that we saw before. So we saw that lambda m is not always an order. Well, it will be precisely when the matrix M is min tropically idempotent. A lattice will be stable if and only if that inequality will be satisfied. So you see, very compact now. We saw earlier that the stable lattices are parametrized by the integral points of the associated polytrope. And it is also true that lambda m is the intersection of all the endomorphism ring of the stable LU lattices. So it is closed. I forgot to say one thing that is important earlier when I defined closed orders, that as we will see, these intersections can always be made finite. Yeah, so think of these intersections as really being finite intersections. And here is another result that is actually quite nice in the sense that if we have a matrix that is min tropically idempotent, so it yields an order, then this polytrope is both min plus and max plus convex. So it means you can take linear combinations with respect to the min sum and you will stay within it. You can take linear combinations with respect to the max sum and you will still land in there. And if we look at the columns of the matrix, these will give us the min plus vertices. I will tell you in a second what these are. And they describe precisely the isomorphism classes of the projective modules. While if we take minus the rows, we get the max vertices and the injective modules. So here is a picture, and I have here a grid because I wanted to draw these guys for you. So you see the min plus vertices are those that I draw there in blue, and they come from taking the columns of the matrix. Now we want to draw everything in the z equals 0 plane. So, I mean, you just have to scale back. In the interest of time, let me just do it quickly. So this is minus 2, 2. This is the min plus, right? And 2, 3, 0. So 2, 3. And we have 0, minus 1. So what would you do in the usual plane? You will draw hyperplanes, and then you will select the half spaces where your polytope lives, and this is how you will build the convex hull of your vertices. Okay, here we do the same. It's just that the geometry looks different. So in this case, the hyperplanes are lines, but a tropical min line, so this is what we want to do now, looks like this. Okay, so this means that I can start from these matrices, take the min convex hull, so with respect to those lines, and recover the polytrope. So that means that here what I do, I take the line through these vertices, okay, then I take the line through these vertices, sorry, and I take the line through these vertices. Okay, and this is how I get my convex hull with respect to these lines. Let's do it with respect to max. Here we have different vertices. So we have, this one I didn't do, I should have written it down. So that is 2, 3. So then I have to go back and do minus 1, 3. And then I have 2, 1. 2, 1. And then the other one is 0, minus 1. So I have minus 1, minus 1. Minus 1. Minus 1. And here, there's something that is not quite right with my picture.
Maybe minus 2, minus 1?
Minus 2, minus 1. Thank you so much. Yeah, they should be off by one. Thank you so much. And here, I told you these min and max operations, they are dual to each other. So here, the tropical lines look like this. And so if I take the max convex hull, this is what I get. Okay, so this result also tells us that if we want to write lambda m as an intersection of endomorphism rings, we can do it either by taking the min vertices or the max vertices. And so this will always be an intersection of at most d endomorphism rings. All right. So I promised you Bruhat-Tits buildings. Let's go there. So what is a Bruhat-Tits building? Now we have a little break from the lattices, well, from the orders, but lattices are in there. And there's more general ways of defining this, but for Bruhat-Tits buildings, I will just give you the lattice class model. So we have K, we have D. So this is the Bruhat-Tits building BDK is an infinite simplicial complex where the zero simplices are given by homotety classes of lattices in K to the D. And a simplex will be given by a chain L1 up to LS, which contains P L1 up to reordering and choosing representatives. Okay, so you can think of maximal simplices as being flags, maximal flags over the residue field. And so when we looked at graduated orders, we were looking at diagonal lattices. So this means we fix a basis, and this, in the language of buildings, means we live in one apartment. And exactly. But what we want to do, we want to work with other orders too. So what is not so difficult to prove is that if we take lambda to be a generic order, then the collection of stable lattices will always be a non-empty, convex, and bounded subset of the building. So convex means take any two lattices. I told you before they will always have compatible bases, so they live in one apartment. Take the graduated order associated to it, so the intersection of their endomorphism rings, and take the stable lattices that live between there. So this is what it means to be convex. Bounded, it means that it will be contained in a bowl. So if the residue field is finite, this also means that the set is finite, but if the residue field is not finite, then it means just that it's contained in a bowl. So this was full pandemic times when we started working on this. So the way we were thinking of this is like, okay, if we're allowed to go out of one apartment, if we're not quarantined in it, what does life look like? And more mathematically said, well, what convex objects arise in the building as stable lattices of closed orders? So we know, now the case of apartments, we know completely, these are the graduated orders, but if we move outside of the apartment, we don't know. Okay, so here is just to give you a picture of what buildings look like in small dimensions. So if you take d equal to 2, you always get a tree. So this is a tree for k equal to q or q2 with a 2-adic valuation. And that is with the same pair, the case where d is equal to 3. An apartment here is an infinite branch. Okay, all infinite branches give rise to R apartments, so give rise to a choice of bases. And there, the apartments are the two-dimensional sheets that you see. So you can think of buildings as being gluings of these apartments. And if you want to see more pictures, there is a very nice link where you can see more buildings, spherical, affine, etc., etc. All right, so I spoke about bowls, about these sets being bounded. So what does it mean to live in a bowl? Well, I have to give you a distance first. So I will say that two lattices have distance, say, s in the building. If I start with the first one, and then I start taking powers, translations of this lattice by a power of the uniformizer, until in that quotient I can see a representative of my other lattice. So in some sense, it's the tighter way of squeezing the second lattice in a quotient of how do I say, subset of the first one and containing a translation of the first one, okay? So this is the distance, and so well, you can write it in those ways, but this is the intuitive idea. And what is nice is that I told you that if we fix a basis, then we work in one apartment, and then there we know that we have tropical geometry playing a role. So if I take a bowl, take the building and intersect it with one apartment, then this distance agrees with the tropical distance in the apartment. So that's very nice. And for d equal to 2, we spoke about trees. Well, that also agrees with the graph distance for d equal to 2. So this is a very good concept of distance. And as usual, we can define both. And we will be interested in both centered in the standard lattice. I mean, anyway, we can translate these and move them around by choosing bases, so it doesn't really matter. So a ball of radius r will be all the collection of all lattices at distance at most r. And as you see, the important radii are really those that are integral. And since the distance in the building agrees with tropical distance, then slicing a bowl with an apartment will give you a tropical bowl. So here is a picture, and for d equal to 2, there's a ball of radius 5 in in B2, Q2. Okay. If I wanted to look at tropical balls, here's what they look like for d equal to 3 and d equal to 2. These tropical balls you can get as polytropes. These will always be polytropes associated to the matrix RJD. So JD is the matrix D by D with zeros on the diagonals and ones outside. So this is radius 1. If you want to get a larger radius, you multiply by R. And in those two pictures there give you the spheres, because I didn't draw the standard lattice there. So for d equal to 3 and d equal to 4. Remember, tropically, we go always down by 1 dimension. Okay. And we know also how to count in the balls. So we know precisely how many elements a tropical ball will have, but also a ball in the building. Well, now I'm assuming that the residue field is finite with size q. And in general, what you can do, you can count elements of balls using partitions of R times D. Namely, you're really looking at the elementary divisors and at all the possible conjugates of a fixed one with prescribed elementary divisors. And we also know what the asymptotics look like in the ball, but maybe for the interest of time, I will now not comment too much on that. What is nice, though, is that also balls in buildings turn out to be collections of stable lattices under orders that we call ball orders. And what do they look like? Well, they are subsets of graduated orders associated to the matrix RJD. So again, with the zeros on the diagonal and the R's outside. But in addition, we add equivalences on the diagonal modulo P to the R, where R is the radius. And these are closed orders and have as collection of stable lattices precisely the elements of the ball. And a nice thing is that we can interpret these collections of stable lattices in terms of submodules of the following module over the truncated ring. So we take OK modulo a power of m to the r. And what we can do, we can also take the corresponding quotient of the standard lattice. Okay, then you see by definition, our ball order will operate by just scalar multiplication on this truncated module. So then we can really think of the elements of the ball as all the submodules, modulo moteti, of course, of this truncated module. And this also tells us that if for apartments the concept of convexity was very clear, we take convexity in the sense of tropical geometry, here it doesn't work. You cannot just say, if I have some vertices that, some lattices that generate my ring, my order as intersections of endomorphism rings, then I just take, the geodesics. So in the apartment, any two I connect with the tropical convex set, and then I paste them together. This doesn't work. Because here, what you can do, you can just take the equivalent of a projective basis. Yeah, with d plus 1 element, you generate those. But if you think of a ball, for example, for d equal to 2 and p equal to 2, what we have is that, well, anything that will look like this will generate the ball. But this is much smaller than if you take the geodesic, that is much smaller than the whole ball. And right, and these balls have vertices in the sense that we saw that once we cut with an apartment, we get a polytope, also in the usual sense. And the cool thing is that these vertices correspond to free modules over this truncated ring of rank, well, properly included in this truncated module. All right, so I showed you balls in buildings. I showed you polytropes. We combine these together to the concept of a polytrope. So this is a word we invented for this project. And what does it mean? Well, a polytrope in the building is just Minkowski sum, think of this like this, of a polytrope with a ball. So you take your polytropes, you take your ball of some given radius, and then you fatten it using the ball. Okay, and it turns out that, well, we know exactly what these look like if we intersect with an apartment. But these also are convex subsets of the building that come from closed orders. Yeah, and you see this is really a mashup of taking polytropes and balls, because we still work with graduated orders, but then we add those equivalencies on the diagonal. And this is a theorem we proved that these are precisely, the polytropes are precisely the stable lattices under the polytrope, what we call the polytrope orders. And as a byproduct, we proved that for d equal to 2, all closed orders are polytrope orders. So there exists a basis such that you can write them like that. And this extends a result of 2 from 2011, where he did it for finite residue field, but we don't need this assumption. And you see there is a picture there. If you're in d equal to 2, you take, how you do this is that you take the longest segment that you have, and then you look at the distances, and then you fatten your segment, and this is what polytropes look like for d equal to 2. And since I want to be able to talk very quickly about a project with codes related to this before my time is over, let me just mention the technique that we used to prove this last result is called the radical idealizer process. So what it does, it starts from your order, it takes the Jacobson radical and then the idealizer of it, so the ring, the largest ring in which this is an ideal, and then it keeps going. And the nice thing is that this respects this concept of distance. So going up and down, you always go down by 1 in the radius. So at some point, eventually, with polytrope orders, you end up in an apartment. It's quite nice. Okay, so as I said, so this is, does time allow 5 minutes, 7 minutes of codes? Good. So this is a project that I did on my own. It's, I will speak very briefly about it, but I found it really fun because it brings together different concepts related to Bruhat-Tits buildings, so I wanted to have the chance at least to tell you something about it. And it generalizes the concept of spherical codes in the usual Euclidean sense, but in the case of Bruhat-Tits buildings. So what you do usually in the Euclidean sense, well, you take a sphere, and then you take your code words to live on the sphere. And what does it mean to be a code? Well, we just need a subset of the elements of the sphere that has at least 2 elements, so that we can define what the minimum distance of the code is. We just look at all the pairs or pairs of elements in the sphere that are distinct, and then we look at their distances and we take the minimum. Okay, and a sphere, maybe I didn't stress it enough, but it's really what you would expect. So now you really fix the distance from the standard lattice to be precisely equal to R. And this can be interpreted again in terms of modules. So what you can do, we fix now Q to be the size of the residue field, and we take it to be finite because we want to count things. And we define VR to be this truncated module. So OK to the D modulo PR OK to the D. Okay, so if R is 1, this is a vector space over the residue field. But in general, you just have a module over this finite ring. And if I'm not mistaken, these rings in the field of coding theory are often referred to as chain rings, because the ideals are all contained one in the other. And an element on the sphere of the ball now you can identify with the module, submodule of VR, that does not contain the p torsion, and it's not contained in p times it. So it really stretches over the whole module. Yeah, you see it at every level. And the vertices of BR, I told you if you intersect with the apartments, then you get the proper free submodules over this truncated ring. And this gives us an interpretation of spherical codes in Bruhat-Tits buildings as submodule codes over chain rings. And what is interesting is also that this distance induced by the distance in the building is a new distance, as far as I know, because it does not match the usual subspace distance that is used over vector spaces, say. Okay, and just for what I want to say next, we define the Grassmannian NVR to be a collection of free submodules of VR of rank n. Yeah, so this just generalizes the concept of the usual Grassmannian for r equal to 1. We recover precisely that. And how do we build these codes? Well, we can do the following. We can prescribe a distance, and my distances will be even. So my distance will always look like 2 alpha. And what we can do, we can fix parameters d r alpha. So r is our radius, d is where our ball lives, so the dimension, and alpha is half of the distance. Then we define a Sperner code, or Sperner, I guess he was German, by saying that we pick elements on the sphere that once we take the translation by p to the alpha minus 1, they hit all the elements that live alpha minus 1 steps away in the Grassmannian of half size. So here is a picture. Yeah? In this case, alpha is equal to 3, so we want to achieve distance 6. Okay, so why do we take alpha minus 1? Because, well, we start from the ball of distance 3, and for each representative on the sphere, we walk down by 2, and we hit one of the red elements. So my code will be the blue. The reds are those ones that I need to hit in a surjective manner. And why one less? Because now I'm allowed to travel one more, and I will hit one of the reds again if I do 1 and 1, so plus 2. So this is how you define a code, Sperner code. And why are these nice? Well, these give us a lower bound on the size of an optimal code. So if we know that if a code of prescribed distance to alpha has maximal size, then this size is at least the size of a corresponding Sperner code. And in the extremal cases in which d is equal to 2 or the distance is maximal, so it's 2r, so you really have to travel all the way from one point to the other, then these codes are really optimal. It's the best that we can get. And how do we prove these results? Where in these extremal cases, we manage to reduce them to looking at modules that are really free. So for d equal to 2, these modules on the boundary will always be free modules. But for alpha equal to r, this does not have to be the case, but you can change your code in such a way you deal with free modules, and then you use results from extremal combinatorics to prove that this is the best you can do by looking at anti-chains in Grassmannians. So here's a question. I know that these codes are optimal for alpha equal to r and d equal to 2, but I don't know what happens in general. And I have no ideas how to prove this, so here's an open question. And just in the last minute or two, I just wanted to say that one could also ask what happens if we restrict to one apartment. And this is one-to-one the generalization of so-called permutation codes. So over ball, you can take an element and then say, I just permute the entries and I generate a code like that. And here you can do the same with the exponent vectors. This is exactly the same. So here's a picture. You see the red dots and the blue dots were min and max vertices of our tropical ball for d equal to 4. The yellow ones are vertices in the usual sense, but not tropically. But in this case, those give a larger code than the other ones. So finally, these other vertices get also some merit. And for these codes, since they're purely combinatorial, you can really derive all these relations between the minimum distance and the maximum cardinality that you can have. And here, building optimal codes is easier. The optimal here is much less optimal than what it means in the usual sense. Though the upshot is that encoding and decoding here, it's much faster and much easier to do. Maybe there are other generalizations in one apartment that one could be looking at, and I very much thank you for your attention. This is everything I wanted to say. Here are our archive identifiers of the 3 papers I presented today, or at least bits of them. And there's a math repo page that is hosted by the MPI Leipzig, where we put some code in the more combinatorial aspects of the graduated orders that I didn't have the time to talk about. So have a look if you're interested. Thank you so much.
Thank you very much for this very nice talk and providing us with a whole new vocabulary, I can say. Are there any more questions for Mima? I'll bring the microphone over to you. I was going to ask about the color coding of the pictures you showed earlier, but then you kind of said it on the last slide. But also this big graph that you showed with colors at the edges, is that related to codes, even though you hadn't mentioned them yet?
But this you mean here?
Even before there was, I think.
No,
Oh,
sorry,
no, yeah,
I
it was
went
that
later.
One. Sorry, it was that one. Yeah, that one. Sorry, it was.
Yeah, I mean, these identify again the min-max and the min vertices and the max vertices, so they separate them like that. And yeah, in this case, you see you only get min and max vertices. There are no other vertices. But as soon as you go one dimension higher, then you get also vertices that are not tropical vertices. And
those play a role in your coding?
Exactly, yeah.
Great. Very nice. Yes.
So in the tree case, I think you mentioned this, and I missed it, but in the case of the tree, a path gives you an Eichler order in M2, QP, whatever. Is there a similar analog here for the buildings? Like, can you see other types of orders?
Yeah, so the Eichler orders are the same as closed orders, right? If I'm not mistaken. I think
it's
so.
It's a new word for me.
Yeah. So
intersection of two maximal orders. Yeah.
Two? Just two.
Yeah.
Yeah, these are subsets of the graduated orders. Because the point is that if you intersect two, it means that you're looking at two lattices, right? And these always have compatible bases, so you can always put them in one apartment. So then you're reduced to the easy case somehow, yeah. And then there you can take the geodesic convex hull. So in the case of the tree, it will just be the segment. Mm-hmm. But in higher dimension, you have to take the tropical closure. Yeah, but that's it, yeah.
Thank you.
Thank you. Any more questions? Yes.
In your soft lockdown slide.
Right.
So you're leaving your apartment, but like
Yes.
how far are you going? Do you
Yeah,
know that
this
a
is why
priori?
it's called. This is why it was called the soft lockdown. You're allowed to get out of the house, but in the radius where you stay, you know, if they give you R radius, you're in your apartment, and then you can walk.
So you
up
can
to
visit
that
the neighbors,
radius.
but just up to the
Yeah.
radius you're fixing. Okay.
Right. So you have your apartment, your polytrope in the apartment, and then you just fatten it, but the radius you're allowed to go.
Okay,
away
so the
from your
building
apartment.
maybe, but okay.
Yeah.
Good.
Yep.
So in one of your theorems, you were characterizing projective modules. Can you please, yeah.
This is actually, yeah, I mean, this is a theorem of Pleskin and Tassenhaus. This is just rewritten in terms of tropical geometry.
Yes, so my question is, so can you characterize also invertible modules when, I should have, right, so when you have two lattices, you can define an inverse by taking the order and taking the homes to that order.
Yeah.
Can you characterize, and then you can define a notion of invertible when you land into the lambda m, I would say.
I think I need to think a little bit about
okay.
this, but maybe we can do it
later.
in the break, yeah. Thanks.
Okay. I see no further questions, so let's thank Mima again.
Thank you very much. Thank you.